The Milky Way is so huge it defies what we believed. Everything we thought we understood about cosmic scale shatters when confronted with a single, undeniable fact. Right now, you are traveling through space at 560,000 miles per hour, carried by a structure so massive it challenges the very limits of human comprehension. Not in a rocket ship, not in some distant future. Right now, as you read these words, you are hurtling through the cosmos at speeds that would make every human spacecraft look like it's standing still. You cannot feel this motion. Your coffee sits perfectly still on your desk. The air in your room remains calm. Nothing in your immediate experience suggests you are moving at all, let alone at velocities that dwarf anything humanity has ever built. This disconnect between experience and reality reveals something profound. We live inside something so vast that light, traveling at 670 million miles per hour, requires 100,000 years to cross from one edge to the other. The Milky Way isn't just big, it's so incomprehensibly huge that it forces us to reconsider everything we thought we knew about our place in the universe. We call this the Milky Way. Yet for all of human history, we have never seen it from the outside. We have never stepped back to witness its true dimensions. We exist like microbes living inside a cathedral, able to examine individual stones, but unable to comprehend the complete architecture. For over a century, astronomers believed they had measured our galaxy's size. The number 100,000 light-years appeared in textbooks as settled science. Our cosmic neighborhood seemed well-defined, its boundaries clearly marked. But recent observations have shattered this comfortable certainty. New measurements using cutting-edge space telescopes reveal that we got the size wrong, dramatically wrong. The Milky Way extends far beyond what anyone imagined. Stars belonging to our galaxy have been detected at distances approaching 130,000 light-years from the galactic center. The dark matter halo that dominates our galaxy's mass stretches nearly 2 million light-years into space, 20 times farther than the visible stellar disk. These discoveries force us to redraw the map of our cosmic home and reconsider everything we thought we understood about galactic structure. This revelation raises unsettling questions. If we miscalculated something as fundamental as the size of our own galaxy, what else have we gotten wrong? How can we claim to understand the universe when we cannot even accurately measure the cosmic structure we inhabit? The answers to these questions will take us on a journey through the strangest physics ever discovered. Tonight, we will explore how astronomers finally determined the true scale of our galactic home. We will discover why measuring the Milky Way presents unique challenges that no other astronomers in the universe face. We will learn about the invisible matter that outweighs everything we can see by a ratio of 20 to 1. And we will understand why our position within the galaxy makes us both uniquely privileged and permanently limited in what we can observe. But before we can comprehend how big the Milky Way truly is, we must first understand a more fundamental problem. A problem that reveals why this question proved so difficult to answer in the first place. The problem is this: how do you measure something when you are trapped inside it? Astronauts describe a moment that changes them forever. They press their faces against the small spacecraft window, searching for familiar landmarks below. Cities that seemed infinite from ground level appear as scattered pinpricks of light. Mountain ranges that took days to cross now stretch beneath them like wrinkles in paper. But here's what shocks them most. They cannot see their house. They cannot see any house. From just 250 miles above Earth, individual buildings vanish completely. The resolution of human vision simply cannot capture objects that small from that distance. This reveals something profound about measurement that applies far beyond orbital mechanics. Distance erases detail. From the International Space Station, entire neighborhoods disappear. Cities become fuzzy patches. Countries blend into brown and green smears across the planet's surface. What seemed impossibly large from ground level proves impossibly small from space. This perspective trick works both ways. Just as we shrink when viewed from above, the space around us grows more vast than our minds can grasp. That empty blackness surrounding our tiny planet stretches in every direction for distances that make the width of Earth seem like a grain of sand on an endless beach. Now imagine trying to measure the beach while you are the grain of sand. This is our exact situation with the Milky Way. We face a challenge that no other astronomers in the universe encounter. Every other galaxy can be photographed from the outside, mapped in its entirety from a comfortable external vantage point. We alone must piece together the structure of our cosmic home from clues gathered while trapped within its boundaries. When we look toward the galactic center, we peer through a disk packed with stars and dust. Thick clouds of interstellar material block our view like fog, absorbing visible light before it can reach our telescopes. We can see only a few thousand light years through this cosmic smog before everything disappears into darkness. Think of mapping a vast city while locked in a basement apartment with no windows. You could send observers to different street corners to report what they see. You could measure distances between known landmarks. You could calculate building heights from shadows. But you could never step back to view the whole metropolitan area from above. You would spend decades piecing together fragments, always wondering if your map matched reality. This limitation plagued astronomers for centuries. They knew we lived inside a collection of stars. They could measure distances to nearby stellar neighbors. They could observe how stars clustered more densely in certain directions. But determining where our galaxy ended and empty space began proved nearly impossible from our position within the structure. The breakthrough required a clever trick. If you cannot measure something directly, measure something else that reveals the truth indirectly. Harlow Shapley understood this principle when he began his revolutionary work. In 1917, Harlow Shapley did not set out to measure the Milky Way. He set out to understand globular clusters, those ancient balls of stars that hover around our galaxy like fireflies around a campfire. Each cluster contains hundreds of thousands of stars packed into spherical formations so dense that their cores shine with the combined light of a small galaxy. Shapley noticed something peculiar about these clusters. They did not distribute themselves evenly across the sky. Instead, they concentrated heavily toward one particular region in the direction of the constellation Sagittarius. This asymmetry suggested something profound. Either we sat at the center of the cluster distribution and they all happened to gather on one side, or we occupied an off-center position. Within a larger structure, the second possibility intrigued him. If globular clusters orbited the true center of our galaxy, their distribution would reveal where that center lay. The clusters would act like survey markers, defining boundaries we could not see directly. But this required solving an even harder problem. How do you measure the distance to objects tens of thousands of light years away? Standard surveying techniques fail completely at such scales. Triangulation works only for nearby stars. Beyond a few hundred light years, parallax angles become too small to measure accurately. Shapley found his answer in Cepheid variable stars. These remarkable stellar objects pulse brighter and dimmer, with clockwork regularity, some completing their cycles in days, others taking months. Henrietta Swan Leavitt had discovered something extraordinary about these stars. The rate at which a Cepheid pulses directly correlates with its true luminosity. Slow pulsars shine intrinsically brighter than fast pulsars. This relationship handed astronomers a cosmic measuring stick. When Shapley observed a Cepheid variable, he could time its pulsation period to determine its actual brightness. Then he compared that true brightness to how dim it appeared from Earth. The difference revealed distance because light dims predictably with distance according to the inverse square law. Using this technique, Shapley measured distances to dozens of globular clusters. When he plotted their positions in three-dimensional space, a stunning pattern emerged. The clusters outlined a vast spherical halo roughly 100,000 light years. Across, our solar system sat nowhere near the center. We occupied a position about 2/3 of the way toward the edge, roughly 30,000 light years from the galactic core. This measurement shocked the astronomical community. 100,000 light years exceeded every previous estimate by enormous margins. Most astronomers had assumed our galaxy stretched perhaps a few thousand light years across. Shapley revealed that we inhabit something cosmically immense, a structure so vast that light requires 100 millennia to traverse it. His discovery also demolished humanity's last claim to cosmic centrality. Earth does not sit at the center of the solar system. Our sun does not occupy the center of the galaxy. We exist in the galactic suburbs, in a quiet backwater far from the action at the core. This demotion stung, but it liberated us to see the universe as it truly exists rather than as we wished it to be. Shapley's measurement held up remarkably well. Modern techniques refined his estimate slightly, but he captured the basic scale correctly using instruments that seem primitive by today's standards. His 100,000 light-year figure appeared in textbooks for decades as the definitive answer to our galaxy's size. But Shapley mapped only what he could see. Something invisible surrounds us, and it changes everything. In the 1970s, astronomer Vera Rubin made observations that defied explanation. She measured how fast stars orbit around the centers of distant galaxies. According to Newton's laws, stars far from the galactic center should orbit more slowly than stars. Near the center, just as Neptune orbits the Sun more slowly than Mercury. But that's not what Rubin observed. Stars in the outer regions of galaxies move far too quickly. They traveled so fast that they should fly apart and scatter into intergalactic space like mud flinging off a spinning tire. The gravitational pull from all the visible matter in these galaxies could not possibly hold these speeding stars in stable orbits. Something else had to be out there, something massive, something generating enough gravitational force to keep galaxies from tearing themselves apart. Scientists name this mysterious substance dark matter, not because it appears dark, but because it emits no light whatsoever. Dark matter does not absorb light. It does not reflect light. It does not interact with electromagnetic radiation in any way. The only force it responds to is gravity. This invisible material outweighs everything we can see by a staggering ratio. For every kilogram of normal matter in our galaxy, roughly 20 kilograms of dark matter exists alongside it. Stars, planets, gas clouds, dust particles, and everything else we observe accounts for only 5% of our galaxy's total mass. The other 95% consists of particles we cannot see, cannot touch, and cannot detect with conventional instruments. How do we know it exists if we cannot observe it directly? The same way we know wind exists when we cannot see air. We observe its effects on other things. Stars orbit too quickly. Galaxies rotate too fast. Light bends around galaxy clusters more than it should based on visible mass alone. Every observation points to vast quantities of invisible matter distributed throughout space. This dark matter forms a roughly spherical halo around our galaxy, extending far beyond the visible disk of stars. Recent measurements reveal this halo stretches nearly 2 million light-years from our galactic center. 2 million light-years, 20 times farther than Shapley's visible boundary, 20 times larger than the galaxy we thought we knew. Think of a flashlight beam in a dark room. The visible stars in our galaxy represent the bright cone of light. The dark matter halo represents the entire room surrounding that small illuminated region. We live inside the beam, completely surrounded by vast volumes of invisible mass that we detect. Only through gravitational influence, this discovery fundamentally changed how we think about galaxies. The visible spiral we see in photographs represents merely the bright center of something vastly larger and almost entirely invisible. Most of our galaxy consists of empty space filled with mysterious particles that pass through normal matter as if it were not even there. The distances between objects in our galaxy create a kind of cosmic loneliness that defies human comprehension. Light from our nearest stellar neighbor, Proxima Centauri, left that star over 4 years ago. 4 years. The photons reaching your eyes right now began their journey when different songs topped the charts, when different leaders governed nations, when the world looked fundamentally different than it does today. This 4 light-year gap represents the closest another star gets to our sun. In cosmic terms, Proxima Centauri qualifies as our next-door neighbor. But this neighborhood stretches across distances that make interstellar travel seem like fantasy rather than engineering challenge. If you could drive a car at highway speed toward Proxima Centauri, the journey would require 40 million years of continuous travel. 40 million years. Agriculture, writing, cities, empires, industry, and space exploration all developed during a time span much shorter than the drive to our closest stellar neighbor. The Voyager 1 spacecraft, humanity's fastest and most distant creation, races away from our solar system at 38,000 miles per hour. This velocity would cross the United States in less than 5 minutes. Yet even at this incredible speed, Voyager would require 73,000 years to reach Proxima Centauri if it were headed in that direction. 73,000 years exceeds the entire span of human civilization by a factor of 7. Every pyramid built, every empire risen and fallen, every war fought, every discovery made happened during a time frame shorter than the journey to the next star over. But reaching our nearest neighbor represents barely the first step in galactic exploration. To cross the full width of our galaxy would require Voyager 1.7 billion years of constant travel. 1.7 billion years. When such a journey began, the most advanced life forms on Earth would have been simple bacteria, multicellular. Organisms had not evolved. Animals did not exist. During the time required to cross our galaxy at humanity's fastest speed, life evolved from single cells to the complexity of human consciousness. This reveals something profound about the nature of our cosmic home. The Milky Way is not a crowded metropolis where stars jostle for position. It's a desert of emptiness punctuated by occasional islands of matter separated by distances so vast that traversing them exceeds the timescales of biological evolution. The space between stars contains less than 1 atom per cubic centimeter. This represents a vacuum more complete than anything we can create in laboratories on Earth. Voyager travels through regions so empty that it might not encounter another solid object for millions of years. Yet despite this crushing isolation, our galaxy contains 400 billion stars. 400 billion. Points of light scattered across such enormous volumes that most of them will never gravitationally influence each other. Most stars will live their entire lives, burn through their nuclear fuel, and die without ever coming close enough to another star to significantly alter its trajectory. We exist in a galaxy that is simultaneously unimaginably vast and profoundly empty. This paradox defines the structure of our cosmic home. At the exact center of our galaxy lurks something so dense and massive that it warps the fabric of spacetime itself. Sagittarius A. The supermassive black hole at our galactic core contains the mass of 4 million suns compressed into a region smaller than Mercury's orbit around our sun. 4 million suns worth of matter packed into a space you could cross in minutes if you could somehow survive the journey. This gravitational monster exerts such powerful attractive force that it holds our entire galaxy together, binding 400 billion stars into a single rotating structure. Without this central anchor, our galaxy would gradually disperse, its stars drifting away into the cosmic void like dandelion seeds on the wind. A black hole this massive creates effects that defy everyday experience. Near its event horizon, the boundary beyond which nothing can escape, space itself gets stretched and twisted into impossible geometries. Time runs slower than it does here on Earth. A clock placed near Sagittarius A would tick more slowly than an identical clock in your living room. This is not science fiction. This is Einstein's general relativity in action, confirmed. By countless experiments, we cannot see the black hole directly because it traps light along with everything else that ventures too close. But we can observe its effects on nearby objects with stunning precision. Stars that orbit close to Sagittarius A reach speeds exceeding 3,000 miles per second as they whip around the invisible gravitational anchor, 3,000 miles per second. These stars complete orbital periods measured in years, not centuries, despite orbiting an object 26,000 light-years away from us. Astronomers have tracked individual stars as they swing around Sagittarius A in elliptical orbits, watching them accelerate to incredible velocities at closest approach before slowing down as they move away. One star, designated S2, completes a full orbit in just 16 years. Its motion provides some of the most precise measurements of relativistic effects ever obtained, confirming Einstein's predictions with remarkable accuracy. The black hole occasionally feeds when gas clouds or unfortunate stars wander too close to its gravitational grasp. As a material spirals inward toward the event horizon, friction heats it to temperatures of millions of degrees. This superheated matter glows brilliantly in X-rays and radio waves before disappearing forever beyond the point of no return. These feeding episodes can briefly make our galactic center shine with the luminosity of billions of stars. Recent observations reveal that Sagittarius A spins at nearly the maximum rate possible for any black hole. It rotates so fast that it literally drags space itself along with its rotation, creating a phenomenon called frame dragging. Space near the black hole does not remain stationary. It gets pulled along like water swirling around a drain. This central engine likely formed early in our galaxy's history, growing from a smaller seed by consuming gas, dust, and stars over billions of years. As it grew larger, its gravitational influence expanded, allowing it to capture and organize the matter that would eventually become our spiral galaxy. In a very real sense, Sagittarius A built the galaxy we call home. Our solar system does not orbit the galaxy like a record spinning on a turntable. Records spin as solid objects, every point completing one revolution in the same amount of time. The inner grooves and outer edge rotate together, maintaining their relative positions. But galaxies behave differently. Stars closer to the galactic center orbit much faster than stars farther out, like runners on a track where the inside lanes move at higher speeds than the outside lanes. This differential rotation creates a complex pattern of stellar motion that reshapes our understanding of galactic time. Our solar system, positioned roughly 26,000 light-years from the galactic center, requires 250 million years to complete one orbit. 250 million years. Astronomers call this span a cosmic year, and it provides a useful measure for galactic timescales. Since Earth formed 4.5 billion years ago, our planet has completed only 18 trips around the galaxy, 18 cosmic years. All of Earth's history, from the formation of the first rocks to this present moment, spans less than 20 galactic rotations. Consider what this means for the history of life. When Earth completed its previous orbit around the galaxy 250 million years ago, the supercontinent Pangaea was just beginning to break apart. Dinosaurs had not yet evolved. The most advanced life forms were primitive reptiles and amphibians. Mammals did not exist. Flowers did not exist. Grass did not exist. The entire age of dinosaurs, from their first appearance to their extinction 65 million years ago, lasted about 1/4 of a galactic year. All of recorded human history represents less than 1/10,000th of a cosmic year. If our galaxy's history was compressed into a single Earth year, human civilization would represent the last few seconds before midnight on December 31st. This slow rotation creates profound consequences for our stellar neighborhoods. Stars that currently sit near each other in space will drift apart over cosmic time. The familiar patterns of constellations that seem permanent from human perspectives will completely rearrange themselves within a few million years. The Big Dipper will not look like a dipper. Orion's belt will scatter. Our sun's orbital path carries us up and down through the galactic disk as we circle the center. We spend about 33 million years above the disk's central plane, then dive down to spend 33 million years below it, creating a gentle bobbing motion that takes roughly 66 million years to complete one full oscillation. Some scientists suggest this vertical motion might correlate with mass extinction events on Earth. When our solar system passes through the disk's central plane, we encounter denser concentrations of gas, dust, and debris that could disrupt comets in the outer reaches of our solar system, potentially sending them tumbling toward the inner planets. The timing remains controversial, but the connection intrigues researchers studying Earth's biological history. The beautiful spiral arms that define our galaxy's appearance exist as phantom structures, more like cosmic traffic jams than solid objects. This revelation overturns the intuitive picture most people carry in their minds. Most imagine galactic spiral arms as fixed features, like the arms of a giant pinwheel rotating through space. But this picture proves completely wrong. The spiral arms contain no permanent matter. Instead, they represent zones where stars and gas temporarily crowd together before dispersing back into the general galactic disk. Think of rush hour traffic on a busy highway. Cars bunch up around construction zones or accidents, creating dense concentrations that move much slower than individual vehicles. From an airplane, these traffic jams look like solid structures crawling along the roadway, but no individual car remains trapped in the jam permanently. Cars constantly enter the crowded zone from behind and exit ahead, while the jam itself maintains its shape and location. Our galaxy's spiral arms work exactly the same way. Individual stars orbit the galactic center at their own speeds, occasionally passing through spiral arms like cars passing through traffic jams. The arms themselves represent density waves, compression zones that sweep around our galaxy, creating temporary concentrations of stars, gas, and dust. These compression waves trigger intense episodes of star formation. As they squeeze gas clouds to higher densities, nuclear fusion ignites in thousands of newborn stars. New stars burst into existence in brilliant blue clusters, illuminating the spiral arms and making them visible across vast distances. The brightest, most massive stars burn out quickly, dying as spectacular supernovas before they can drift away from their birthplace. This creates the illusion that spiral arms contain permanent populations of young, bright stars. Our solar system currently sits between two major spiral arms in a smaller spur called the Orion Arm. We completed our last passage through a major spiral arm roughly 50 million years ago, and will not encounter another for approximately 10 million more years. During our keen travels through spiral arms, our solar system experiences higher concentrations of gas, dust, and radiation that might influence Earth's climate and biology. The increased cosmic ray flux could affect cloud formation in our atmosphere. The denser interstellar medium could compress the heliosphere, the protective bubble created by the solar wind. These effects remain speculative but suggest that our galactic environment may shape conditions on Earth in ways we are only beginning to understand. The spiral structure itself rotates around our galaxy much slower than individual stars orbit. This differential motion allows stars to pass in and out of spiral arms over cosmic time. If spiral arms rotated at the same speed as stars, they would quickly wind up into tight spirals and disappear within a few 100 million years. Our galaxy does not travel alone through the cosmic dark. Small, companion galaxies orbit around us like moths circling a campfire, bound by gravitational threads stretching across hundreds of thousands of light years. But this relationship is not peaceful. Our massive gravitational influence slowly tears these smaller neighbors apart in a process astronomers call galactic cannibalism. The two most famous victims shine prominently in southern hemisphere skies. The large and small Magellanic Clouds appear as fuzzy patches of light, looking like detached pieces of our own Milky Way. Early ocean navigators used these celestial landmarks for guidance, never suspecting they gazed at entire galaxies in their own right. The Large Magellanic Cloud contains roughly 10 billion stars and sits 160,000 light-years away. The Small Magellanic Cloud, with about 3 billion stars, lies slightly farther at 200,000 light-years. These distances place both galaxies beyond the edge of our visible stellar disk, but still within our extended dark matter halo. These companion galaxies do not orbit peacefully. Our gravity distorts their shapes, stretching and warping their stellar populations like taffy being pulled. Long streams of gas and stars get torn away from both Magellanic Clouds, creating vast ribbons of matter that trail behind them as they circle our galactic center. These stellar streams wrap around our galaxy like ribbons, marking the slow destruction of our neighbors. The Sagittarius Dwarf Elliptical Galaxy provides an even more dramatic example of this cosmic violence. This collection of roughly 4 billion stars currently passes through our galaxy's disk, being shredded by tidal forces as it attempts to complete its orbit. Over the past few billion years, our gravity has stripped away most of its original stellar population. Computer simulations suggest that within the next few billion years, the Sagittarius Dwarf will completely disappear, its stars fully absorbed into our galactic structure. This process of galactic cannibalism has shaped our galaxy's growth throughout cosmic history. Many stars in our galactic halo likely originated in small satellite galaxies that our gravity captured and destroyed over the past 10 billion years. The smooth distribution of stars in our halo actually represents the blended remains of dozens or hundreds of smaller galaxies. Over 30 smaller satellite galaxies populate our local neighborhood, most containing only a few million stars each. These tiny galaxies bear names like Draco, Sculptor, and Fornax, named after the constellations in which they appear. Many are so faint that we discovered them only recently, using sensitive electronic detectors to pick out their dim glow against background stars. This galactic predation represents a fundamental aspect of cosmic evolution. Large galaxies like ours grow primarily by consuming smaller neighbors rather than by accumulating matter directly from intergalactic space. We are building our galaxy on the corpses of smaller cosmic structures. For decades, astronomers debated whether our galaxy possessed one of the most common features found in spiral galaxies throughout the universe. Most spiral galaxies contain a central bar, an elongated concentration of stars that extends outward from the galactic nucleus like the handle of a cosmic dumbbell. These stellar bars play crucial roles in galactic evolution, channeling gas inward to feed star formation and helping drive spiral arm patterns. But discovering whether our own galaxy contains such a feature proved remarkably difficult. The problem arose from our position within the galactic disk. Dust clouds scattered throughout block visible light, creating a zone of obscuration that prevents clear views of the galactic center. Mapping the shape of a forest while standing among the trees proves impossible when fog fills the spaces between the trunks. The breakthrough came in 2005 when the Spitzer Space Telescope used infrared light to peer through the dust. Infrared radiation penetrates cosmic dust far better than visible light, allowing astronomers to see through the obscuring material that had hidden our galaxy's inner structure for so long. The infrared observations revealed a startling truth. Our galaxy does contain a central bar stretching roughly 27,000 light-years from end to end. This massive stellar structure contains billions of stars arranged in an elongated pattern that rotates as a single rigid body around our galactic center. The discovery explained several puzzling observations about our galaxy's behavior. The central bar helps drive our spiral arm pattern by creating gravitational disturbances that compress gas clouds as they orbit. It channels material inward toward our central supermassive black hole, providing fuel for occasional feeding episodes. The bar acts like a cosmic conveyor belt, moving gas from the outer regions toward the center where it can form new stars or feed the black hole. Our galactic bar rotates faster than our solar system orbits, completing one revolution every few 100 million years. This means different parts of our galaxy periodically align with the bar's gravitational influence, creating waves of star formation that propagate outward through our spiral arms. The bar's existence also affects our galaxy's long-term evolution. As it rotates, the bar slowly loses angular momentum to the surrounding disk, causing it to grow longer and more prominent over cosmic time. Computer simulations suggest our bar formed relatively recently in galactic terms, probably within the last few billion years, through gravitational instabilities in the inner disk. This discovery revolutionized our understanding of our galaxy's architecture. Rather than a simple spiral galaxy with a circular central bulge, we inhabit a barred spiral galaxy with complex internal structure that drives much of the dynamic behavior we observe throughout our cosmic neighborhood. In 2013, the European Space Agency launched a spacecraft that would fundamentally transform our understanding of the Milky Way. The Gaia mission carried no flashy cameras, no spectrometers, no particle detectors. It carried something far more powerful: the most precise measuring instruments ever sent into space. Gaia's mission sounds deceptively simple: measure the exact positions and motions of 1 billion stars. 1 billion. This represents less than 1% of our galaxy's total stellar population, but it's enough to revolutionize galactic astronomy. Traditional astronomy focused on taking pictures, capturing light, analyzing spectra. Gaia pioneered something different: astrometry, the precise measurement of stellar positions and movements. The spacecraft measures stellar positions with accuracy equivalent to spotting a coin on the Moon from Earth. This precision allows astronomers to detect motions that would remain invisible to any ground-based telescope. But measuring position alone provides limited information. The real breakthrough comes from measuring motion. Gaia tracks how each star moves across the sky and, crucially, measures how fast each star travels toward or away from us using the Doppler effect. These three-dimensional velocity measurements reveal the dynamic structure of our galaxy in unprecedented detail. The data revealed something astronomers had suspected but never definitively proven. Our galaxy is not in equilibrium. The disk wobbles, it ripples, it shows signs of recent disturbances that propagate through stellar populations like waves crossing a pond. Gaia detected stars in the outer regions of our galactic disk at distances approaching 130,000 light-years from the center. These distant stellar populations exist far beyond what was considered the absolute limit of our galaxy's structure, extending the known boundaries by tens of thousands of light-years. The spacecraft also mapped stellar streams, those ribbons of stars torn from destroyed satellite galaxies. These streams wrap around our galaxy in complex patterns, recording the violent history of galactic cannibalism. By tracing these streams backward in time using computer simulations, astronomers can reconstruct which satellite galaxies contributed which stars to our galactic halo. Perhaps most importantly, Gaia revealed that our galaxy experienced a major collision roughly 10 billion years ago. A dwarf galaxy containing several billion stars merged with the Milky Way in a violent encounter that fundamentally reshaped our galactic structure. The evidence exists. In the motions of stars throughout our halo, populations that still retain the orbital characteristics they inherited from their parent galaxy billions of years ago. This discovery means our galaxy's history is far more violent than anyone imagined. We are not a pristine spiral that formed smoothly from collapsing gas clouds. We are an amalgamation built from the merger and destruction of countless smaller galaxies over billions of years. Our galaxy is not the stable, perfectly balanced disk that most people imagine. Instead, our cosmic home wobbles and flexes like a spinning coin, slowly losing momentum. The outer edges of our galactic disk warp up and down, creating ripples that propagate inward toward the center like waves on a disturbed pond. This warping motion represents one of the most dynamic and surprising aspects of our galactic structure. For decades, astronomers detected hints of this distortion but could not determine whether it remained stationary or moved over time. Recent observations using variable stars of different ages have revealed that our galaxy's warp precesses, rotating in the opposite direction from our star's orbital motion at roughly 1/200th of a degree every million years. What causes this strange wobbling? The culprit appears to be our dark matter halo. Computer models suggest that our invisible halo has a slightly flattened shape, like a football rather than a perfect sphere. As our stellar disk rotates within this oblate dark matter distribution, gravitational torques create the wobbling motion we observe. Think of a coin spinning on a table. As friction slows the coin's rotation, it begins to wobble, more and more dramatically until it finally falls flat. Our galaxy experiences similar dynamics, though instead of friction, the misalignment between our rotating disk and the principal axis of our dark matter halo creates the torques that drive the wobbling motion. This galactic wobble affects everything within our cosmic neighborhood. Stars in the outer regions of our disk experience vertical accelerations as they ride the warping waves. Gas clouds get compressed and stretched as the disk flexes around them. Even our solar system, though relatively close to the galactic center, participates in this slow cosmic dance. The wobbling motion provides crucial information about the distribution of dark matter around our galaxy. By measuring how the warp precesses, astronomers can infer the shape and orientation of the invisible halo that dominates our galactic mass. This gives us one of the few direct ways to probe the properties of dark matter on galactic scales. Satellite galaxies contribute additional complications to our galactic wobble. The large and small Magellanic Clouds, along with our smaller companion galaxies, exert their own gravitational influences on our disk structure. Their orbital motions create additional torques that modify the precession rate and pattern of our galactic warp. This discovery reveals that our galaxy exists in a constant state of dynamic evolution, continuously responding to gravitational influences from both visible and invisible matter. The galaxy we inhabit today differs from the galaxy that existed 100 million years ago, and will differ from the galaxy that exists 100 million years in the future. 4.5 billion years from now, our night sky will transform beyond recognition. The Andromeda Galaxy, our nearest large galactic neighbor, races toward us at roughly 250,000 miles per hour. This colossal collection of 1 trillion stars will collide with our galaxy in what astronomers call the most predictable cosmic catastrophe. Right now, Andromeda appears as a faint smudge of light in our autumn skies, barely visible to the naked eye despite containing more stars than our entire galaxy. But this seemingly delicate spiral sits only 2.5 million light-years away. In cosmic terms, we practically share the same neighborhood. As Andromeda approaches, its gravitational influence will begin disrupting our galaxy's structure long before the actual collision occurs. Our outer spiral arms will stretch and distort. Streams of stars will get pulled away from both galaxies, creating vast bridges of matter spanning the gap between the two cosmic titans. The night sky will fill with unfamiliar constellations as our foreign stars invade our celestial sphere. The collision itself will unfold over billions of years, a slow-motion catastrophe spanning timescales unimaginable to human experience. Despite containing over 1 trillion stars between them, individual stellar collisions will remain extremely rare. The distances separating stars are so vast that most will pass by each other like ships in the night. The collision will resemble two clouds of fireflies interpenetrating, with gravitational interactions scrambling orbital paths, but few actual physical impacts. Our sun will likely survive this cosmic merger, though its fate remains uncertain. Computer simulations suggest our solar system might get flung into the outer regions of the merged galaxy, or possibly ejected entirely into intergalactic space. Earth may find itself orbiting a star that wanders forever between galaxies with no galactic home to call its own. The supermassive black holes at the centers of both galaxies will spiral inward toward each other during the merger, eventually combining into a single gravitational monster containing the mass of over 45 million suns. This black hole merger will release more energy in gravitational waves than our sun will emit in light over its entire 10 billion year lifetime. The ripples in space-time from this event will propagate across the universe, carrying information about the collision to observers billions of light-years away. The resulting merged galaxy, which astronomers have nicknamed Milky Way, will bear no resemblance to either of its parent structures. Instead of two elegant spiral galaxies, the collision will produce a single elliptical galaxy, a roughly football-shaped collection of stars with no organized structure or spiral arms. The violent encounter will consume most of the gas available for star formation, leaving the merged system largely devoid of the raw materials needed to create new stars. Our entire local group of galaxies, including both the Milky Way and Andromeda, rushes through space toward something massive and mysterious at 600 miles every second. That represents our collective velocity toward a gravitational anomaly astronomers call the Great Attractor. This invisible mass concentration lies roughly 150 million light-years away in the direction of the constellations Hydra and Centaurus, hidden partially behind. The dust and stars of our own galactic disk, the Great Attractor exerts gravitational pull on thousands of galaxies across hundreds of millions of light-years. Its influence reaches so far that it affects the motion of our entire cosmic neighborhood, dragging galaxy clusters and superclusters toward itself like debris caught in a cosmic whirlpool. What could possibly be massive enough to gravitationally dominate such enormous volumes of space? The Great Attractor contains the mass equivalent of tens of thousands of galaxies like our own, concentrated into a region roughly 500 million light-years across. This represents one of the largest structures in the known universe, a gravitational anchor point that shapes the motion of matter across vast cosmic distances. The mystery deepens because the Great Attractor sits partially hidden behind our own galaxy. When we look in that direction, the stars and dust of our galactic disk block our view of whatever lies beyond. Astronomers call this the zone of avoidance, a region where observations become extremely difficult due to obscuration by our own cosmic home. Using telescopes that can see through dust, astronomers have identified several massive galaxy clusters in the direction of the Great Attractor. The Norma cluster, the Centaurus cluster, and the Hydra cluster all contribute to the gravitational pull that affects our motion through space. But even adding up all these visible structures cannot account for the total attractive force we observe. Something else must be out there. Additional mass, possibly in the form of dark matter concentrations or hidden galaxy clusters, contributes to the Great Attractor's gravitational influence. The complete inventory of matter responsible for our cosmic motion remains unknown, concealed behind the veil of our own galaxy's obscuring material. Recent observations have revealed an even larger structure beyond the Great Attractor. The Shapley supercluster, containing thousands of galaxies, may represent the ultimate destination of our cosmic journey. This massive concentration of matter exerts gravitational influence that extends even farther than the Great Attractor itself, suggesting that our motion through space reflects the combined pull of multiple large-scale structures. This discovery reveals that our galaxy does not move randomly through space. We follow gravitational currents established by the largest structures in the universe, passengers on a cosmic river carried along by forces operating on scales that dwarf even our massive galactic home. Our galaxy sits embedded within one strand of the largest structures in the known universe. The cosmic web represents the ultimate architectural framework of creation, a vast network of dark matter filaments that connect galaxy clusters across billions of light years. These invisible highways channel the flow of matter and energy on the largest scales imaginable, creating a spiderweb pattern that spans the entire observable universe. Our galaxy travels along one of these cosmic web filaments, following a predetermined path established by gravitational influences from dark matter concentrations that formed in the early universe. Like a train traveling along invisible tracks, we move through space guided by forces that operate on scales, dwarfing even our massive galactic home. We cannot see these tracks directly, but we observe their effects on the distribution and motion of galaxies throughout the cosmos. The cosmic web filaments form the backbone of cosmic structure, containing roughly 60% of all matter in the universe. These filaments stretch between massive nodes where thousands of galaxies cluster together, creating a network that resembles neural pathways in a vast cosmic brain. Empty voids containing almost no matter separate the filaments like spaces between brain cells. Computer simulations reveal that this web-like structure emerged naturally from tiny density fluctuations in the early universe. Over billions of years, gravity amplified these initial irregularities, causing matter to flow along preferential directions and creating the filament pattern we observe today. Galaxies formed at intersections and along the lengths of these dark matter highways. Our local group of galaxies, including both the Milky Way and Andromeda, travels along a filament that extends toward the Virgo cluster, a massive collection of over 1,300 galaxies located roughly 54 million light-years away. This filament provides the gravitational framework that guides our motion through space and connects us to broader cosmic structure. The filament we inhabit contains not only galaxies, but also vast reservoirs of hot, ionized gas filling spaces between galactic neighbors. This intergalactic medium, heated to temperatures of millions of degrees, glows faintly in X-ray light and provides raw material for continued galaxy formation and growth. Recent observations have begun mapping the cosmic web directly by detecting this hot, intergalactic gas and measuring subtle gravitational lensing effects created by dark matter filaments. These studies confirm that our galaxy travels along one of the universe's fundamental structural components. The cosmic web also influences our galaxy's evolution by regulating the flow of matter between galactic and intergalactic environments. Gas falling into our galaxy along the filament provides fuel for continued star formation, while galactic winds driven by supernovas and stellar radiation can escape along these same pathways. The boundary of our galaxy refuses to stay put. For decades, astronomers assumed our galaxy's stellar disk ended at a well-defined edge roughly 50,000 light-years from the galactic center. Beyond this point, they expected only empty space populated by occasional globular clusters or stray stars. Recent observations shattered this assumption. In 2018, astronomers using data from the Gaia space mission discovered stars belonging to our galactic disk at distances of 84,000 to 103,000 light-years from the center. These distant stellar populations exist far beyond what was once considered the absolute boundary of our galaxy's structure. Follow-up studies pushed the detection of disk stars even farther. Stars with chemical compositions and orbital characteristics matching our galactic disk have been identified at distances approaching 130,000 light-years from our galactic center. This means our galaxy stretches significantly beyond the canonical 100,000 light-year diameter that appeared in textbooks for over a century. But the stellar disk represents only part of the story. The true boundary of our galactic domain extends far beyond any visible stars. Recent measurements of our galaxy's dark matter halo reveal it stretches nearly 2 million light-years from our center. 2 million light-years, 20 times farther than the visible stellar populations. 20 times larger than the galaxy. We knew this extended structure creates profound questions about where our galaxy ends and intergalactic space begins. If our dark matter halo stretches 2 million light-years while Andromeda's halo extends a similar distance, the two halos likely already overlap. In this sense, the collision between our galaxies may have already begun at the level of dark matter, even though stellar populations will not merge for another 4 billion years. Gravitational interactions with satellite galaxies help explain some of these extended stellar populations. As our gravity tears apart smaller companion galaxies, their stars scatter across vast volumes of space. Some of these disrupted stellar streams could account for the distant stars we now observe in our galaxy's outer regions. The continuing expansion of our galaxy's known boundaries reflects improvements in observational technology and data analysis techniques. Each new generation of telescopes and space missions reveals previously hidden components of our cosmic home, pushing the frontiers of the known ever farther outward. This pattern suggests our galaxy's true extent may be even larger than current measurements indicate. We may continue discovering stellar populations at greater and greater distances as our instruments improve and our surveys reach deeper into space. If we could somehow travel outside our galaxy and look back, we would witness one of the most beautiful sights in the universe. Our cosmic home would appear as an elegant barred spiral galaxy, its sweeping arms glowing with the light of billions of stars arranged in graceful curves extending outward from a bright central bulge. Blue-white clusters of young massive stars would illuminate the spiral. Arms like beacons, while the warm yellow glow of older stars would fill the spaces between with subdued radiance. The central bar would stretch across the galaxy's heart, its elongated concentration of ancient stars rotating slowly around the supermassive black hole at our galactic core. From this impossible external vantage point, we could observe the faint halo of globular clusters surrounding our galaxy like scattered jewels. The extended dark matter halo would remain invisible, detectable only through gravitational effects on nearby objects. Our galaxy's disk would appear remarkably thin when viewed edge-on, resembling a cosmic pancake with thickness less than 1/50th of its diameter. But we will never enjoy this external perspective. We remain forever trapped within our galactic home, like creatures living their entire lives inside a vast cathedral, able to examine individual architectural details but never able to step outside and appreciate the building's complete design from a distance. This limitation defines the human condition on cosmic scales. We inhabit something far grander than ourselves, yet we can never fully comprehend its beauty or complexity because we cannot escape our position within it. We must piece together our galaxy's appearance from fragments and clues, like archaeologists reconstructing an ancient temple from scattered stones. Yet despite this limitation, we have succeeded in mapping our galactic home with remarkable accuracy. Through careful observations, computer simulations, and comparisons with external galaxies, we know we inhabit a barred spiral galaxy, spanning over 130,000 light-years of visible stars, surrounded by a dark matter halo extending nearly 2 million light-years into space. We know our galaxy contains 400 billion stars, at least 100 billion planets, and participates in the grandest cosmic dance imaginable. We orbit a supermassive black hole 26,000 light-years away, completing one galactic year every 250 million years. We travel through space at 560,000 miles per hour, following gravitational currents established by the largest structures in the universe. We are citizens of infinity, residents of a cosmic city beyond all human comprehension. We exist on a tiny rock orbiting an ordinary star in the suburbs of a typical galaxy. Yet through the power of observation and reason, we have mapped the boundaries of our cosmic home and understood our place in the vast architecture of space. The question, how big is the Milky Way, no longer has a simple answer. The visible galaxy spans 130,000 light-years. The true boundary extends 2 million light years, and we continue discovering that our cosmic home reaches farther than we ever imagined